Alright, so let's start a completely new topic, right? So we'll talk about shortest paths. In particular, we'll talk about this very famous single source shortest path problem. Okay. So it's quite possible that many of you know this problem and the associated algorithm, but I will definitely present something which is novel to you, right? So that it will increase your understanding of the topic. So what is a single source shortest path problem? The input consists of a directed graph G and S belongs to the vertex set of D. It's called a source. The output, you want a data structure, right? A data structure containing shortest path from S to each other vertex. This is what I want you to output. Fine. All right. So let's do the easiest one first. Right. Okay. By the way, the edge also has a weight function W from E to, and in this case I am going to focus only on edge weights as positive integers. Fine. Okay. So let's quickly write out eliminate the easy case. So if the edge weight is a constant function, W of E is 1, can you give me an efficient algorithm? BFS, right? So that's quite obvious. So you start at S, right, and do a BFS, and so on and so forth. It's a directed graph, right? So this is not just the tree arc orientations, but it is also the orientations in the given directed graph, right? The vertices are organized into layers. This is layer number 1, their distance from the source is all 1. This is layer number 2, the distance is all 2, and so on, right? And therefore, induction on the layer number, you can prove that the layer number is indeed the distance of the vertex from the source, right? So I am not writing this statement down. The proof of correctness of this claim is proved by induction on the layer number of a vertex. Fine. Okay. Now, what I am going to try and show you before I do this very popular Dijkstras algorithm is that you can come up with what I call a physical algorithm, which will also compute the single source shortest path, right? To understand Dijkstras algorithm, I would always say this is the way to think of Dijkstras algorithm instead of the code that you see in your textbook, especially because the edge weights are positive. You look at the graph and consider the bead thread mesh, right, of the given graph. What do I mean by a bead thread mesh? Simply for every vertex you put this big fat bead, right, out of which we make necklaces, and for every edge you create a thread, right. The length of the thread is some number proportional to the edge weight, right. Let us say it is exactly the edge weight. Let's not worry, right? Even if it says 1000, let us assume the 1000 units, right, of that thread we will cut and make that the edge weight. Fine. So now this bead thread mesh is very well defined. Now instead of running Dijkstras algorithm on a computer, you take this bead thread mesh by S. Right. Fine. That is, what do? You take this mesh and hang it in a high enough ceiling, right? Maybe from some sufficiently high place. Now I want you to tell me, which edges do you think are on shortest paths? So let us say that one of you does this experiment, and your neighboring friend takes the graph and runs Dijkstras algorithm on it, right? And both of you are comparing the data structure output by Dijkstras algorithm with your physical algorithm, right? So let us assume that your friend has, starting from S, right? So maybe this is the shortest path structure he has, right? So let us give names. Let us say A, B, C, D, E and F. Right? What will be the nature of the thread going from S to A in your physical algorithm's output when you hang it from the top? Remember, it's a thread, right? What will it be looking like? Will it be hanging loose? So will it look like this, right? So whatever you have hung here, this is this bead S, and then there is A here, right? Will this fellow be hanging like this? Will the rope be hanging like this? The intuition says it won't be hanging like this, it will actually be tight, because that is indeed the shortest path data structure that the tree is also calculated. Every other path from S to A is actually of a longer length. That's why, so when you hang this, right, the shortest paths become tight, right, or the threads which form the shortest paths will all be stiff and they will be stretched, whereas the paths which don't correspond to shortest paths will all be hanging and they will be loose, right? And actually, if you go look at Dijkstra, that's exactly what the data structure implements, right? And that we will prove just now. Fine. The taut threads are on the shortest path from S. Fine. Right. So this is the intuition. Now let's just convert this. So you can also see that this also makes this physical algorithm, which is exactly going to be Dijkstra's single source shortest path algorithm, a very natural extension of breadth first search. Right? Breadth first search exactly does this, right? You just simply you start at the vertex and then keep layering vertices, right? This physical algorithm also assigns layers to vertices, but the layer of a vertex is related to the length of the path, right? Fine. So now let us just go to the formal specification of the Dijkstra's algorithm. Right? Right? So V0 is S, right? So the starting point is quite nice. You maintain a set, right? at any iteration you have I and you have S and some vertices, let me say V1, V2 to Vi, and the nice property is that you have found the distances from S to every other vertex, right, and you have kept a shortest path. Fine. So now what do you do? The first step is to update right. So what is a picture? You have S and you have the shortest path information to a whole set of vertices, and now there is a set of vertices for which you have not calculated the distance estimate, right. So you look at this particular vertex, right, and now you are going to update the distance estimate. How are you going to update the distance estimate? Using a crucial property of the shortest path, that if you have the shortest path between 2 points, then you actually have the shortest path between every pair of intermediate points on the shortest path, right. So therefore, if you have, this is a crucial property, if you have x and y, and this is a shortest path from x to y, it is not possible that from this vertex to this vertex, you actually have a shorter path in the network. This is indeed the shortest path. If it was a shorter path, then if you go by that shorter path, then the distance from x to y is also lesser than what you claimed as a shortest path. Fine. So this is the structure of a shortest path. So this is a very crucial structure to keep in mind. Subpaths of shortest paths are shortest paths between their endpoints. Fine. Something that I am sure all of you know, but this is a crucial point. Using this, we will update the distance estimate to this particular vertex, right, from S. So what will you do? You probably have a distance estimate. So you will say, okay, what is the shortest path from this vertex to this vertex? What is the shortest path from this vertex to this vertex? What is the shortest path from this vertex to this vertex? What is the shortest path from this vertex to this vertex, this vertex to every vertex to which you have found the shortest path? You use that path, take one more edge if it is possible, and ask what is the length of that path. Among all of them, you pick the cheapest. That will be the distance estimate for this particular vertex, right. So therefore, the distance estimate for, relax for you is min overall I, okay, min overall j going from 0 to I. 0 means S, okay, V0 is, V1 is 1, Vi is I, j going from 0 to I. The distance which you have already calculated from S to Vj plus the weight of the edge from Vj to U. Fine. This is the updated distance estimate at the end of after the ith iteration. That is, at the end of the ith iteration, you update the distance estimate to all the vertices for which you have not yet found the shortest path, right. In the I plus 1th iteration, so you have this relax array, you updated it at the end of the ith iteration. When you enter the I plus 1th iteration, you look at the relaxed data structure and pick that vertex which has the minimum relaxed value. Vi plus 1 is equal to Vi union U. Fine. Now it is quite clear that this is the shortest path from S to U. There cannot be a shorter path because of the fact that your relax estimate use the shortest paths and with one step. Fine. If you ask, is it possible that there is a path of length 2, right? After going from, so let's complete the argument. So starting from S, with one hop, U is the fellow which is closer, right? If somebody says, no, going through one edge is not the cheapest, actually if I went from here to here, take this one edge path to maybe W, and then I take one edge from W to U, this is actually cheaper. If somebody says that, what is your counter argument? Exactly, right? That relax of W would have actually been smaller than relax of U because all the edge weights are positive, right? So you would have actually chosen this and you would not have chosen this actually. This completes the proof that this step in the I+1th iteration is the correct step and you've got the correct distance, right, to U. Fine. That completes the whole proof, right? We only need to study the running time. Right. How many times do you use an edge to update the relax value? So we are trying to measure the running time. To measure the running time, I am asking, look at every edge and ask, how many times did I add this edge weight? So I'll focus just on one edge. How many times did I add this edge weight to the distance estimate of U? At most once, right? Because you use that particular edge, right, when you found the distance estimate for this particular vertex. Of course, if you are not careful and if you are not clever, right, you may actually do a very careless distance estimate repeatedly, right, of U, which is not necessary, right. So if you look at this particular step, right, if you are careless, you may repeatedly do this estimate, right. But observe that distance from S to Vj does not change, right. So this term you should not unnecessarily calculate again and again, right. So just by being a little careful, you can ensure that the edge weight gets considered for addition by the relax estimate, right, at most one time. Fine. So therefore this accounts, so therefore any edge, right, so let us say Vu, right, considered at most one time. Fine. So therefore this contributes an effort of order of m, right. So observe that this is a very careful way of calculating the total effort taken here, right. I am just saying that the time taken for you, the total number of relax estimates that you actually do, it's actually equal to the total number of edges in the graph. Fine. Then you have to pick this fellow. You have to pick the minimum weight element from the relax array, right. That you can actually use a data structure like a min heap or something like that, which I have not explained, but this is a data structure where you can pick the minimum element in constant time and you can update the data structure again to keep the minimum quickly accessible in log n time. Fine. This would be an n times log n. Now this is also nice to look at it a little bit, that observe that the difference between BFS and this algorithm is just this multiplicative factor of log n which is there. Right? As in BFS, if there were no edge weights, then it is order of m plus n. It is order of m plus n log n here. Right? So that's about it. So therefore, we've used therefore Dijkstras single source shortest path algorithm. Relax back. So what happens if there are negative edge weights? So will the algorithm work when you have negative edge weights? For example, I am going to suggest the following idea. Right? So look at all the edge weights and let us assume you have negative edge weights. Add a constant to all the edges, make all the edge weights positive. Right? So if you have, right, here is an attempted idea. Right? So all the edge weights are negative. So let us say you have W1, right, up to Wm, these are all the edge weights. Right? You modify, keep the same graph, simply add W1 plus a constant C plus Wm plus a constant C. Choose the constant carefully so that all these values are greater than or equal to 0. And run Dijkstras. Are you guaranteed to have found the shortest path? Single source shortest path? Okay, now give me an example where this idea will fail. Right. So I hope you heard what he said. So basically he said that if you had paths with lesser number of edges, right, then the constant C gets added only a few times, but if you have longer paths, then the cos C gets added many times, right? And therefore there is no guarantee that you keep an order, right? So if you had shortest path information, right, and if you had organized them, right, in increasing order, right, that order is no longer going to be respected, right, because you added a constant to every edge weight. Fine. Okay. What if there are no negative weight cycles? So let us consider a graph which has negative edge weights but no negative weights, no negative weight cycles. It is not well defined. Therefore, it does not make sense to even talk about the shortest path, right, via Dijkstras single source shortest path algorithm. Right? So, what if the graph does not have negative weight cycles? So, I claim that the algorithm still works. Right? So, claim and in this case we are specifically talking about negative weight, right, directed cycles. Right. So, all that I have said so far, right, works for directed graphs, right, and if you don't have negative weight directed cycles, then the distance estimates that you get, right, are strictly decreasing, right, are monotonically decreasing values. So the reason for this claim is that ds is monotonically decreasing and once it does not reduce again, right. So the key property is that the property of the algorithm is that the relax function ensures that the distance value, the estimate of the distance from S, right, will always be, will never increase, it's monotonically decreasing, right. And once you select a vertex and add it into this set, right, to which distances from S has been found, the distance does not decrease again. Right. So therefore, the point is that Dijkstras works in a slightly more general setting, right, provided you don't have negative weight cycles. So basically, I'm close to finishing. So here is a whole set of questions. Right. So the first one is, so how to discover if the graph G has a negative weight cycle? Because if you have to choose to run Dijkstras algorithm, you need to know whether the graph has a negative weight cycle. So here is one question which is closely related to the shortest path problem. Edge weights are there, how to discover if the graph has a negative weight cycle? Second question is that how to efficiently use the structure of shortest paths to design a data structure that has all pairs shortest path information. So observe that so far what we did was we designed a data structure which has single source shortest path information starting from S, right, and going up to V, right. So the easy data structure, easy idea is to use this single source shortest path data structure n times. So therefore you can do this using n into m plus n log n time. Right. Run Dijkstra from each vertex and keep distance estimates, right. So can we do better? So observe that to check if a negative weight cycle is closely connected to yesterday's tutorial question of find the shortest cycle. So these are all quite related problems. So that's basically what this class of problems is what Meghna will look at when she presents next. So I'm done. So we'll meet again in one lecture's time where we will study another class of graph theoretic questions called vertex cover and matching problems. Yeah.
T2 is a negative path of length -4, for example. So then Dijkstras won't work with this now because even though it's not a negative edge cycle, Dijkstras will pick S2A as 2 instead of it being 0.
Yeah, so I think I made a mistake. So I'll just correct this. Right. So this won't work even in undirected graphs. So let me just go back and so I will just take this back, right? So this claim, I think this claim is wrong, right? I'm sorry for this. Right? And the reason is that this part of the claim is correct, right? And if one applies this carefully, I think, so I said that once u is added, its distance does not reduce again, its distance does not change by the design of the algorithm. So let me just correct myself, right? So negative edges are a problem. So let me just correct this, right? So A gets added into the distance, the vertices to which distance is being found first, right? Now, we never relax the distance estimates for the vertices for which distance has already been found, but there is a very negative weight edge here which brings a path of length 0 here, right? So therefore, it's not just negative weight cycles but also negative weights, right? So right? And this is also probably an example where if you just scale up all the edge weights, you will not get the shortest path, right? So for example, this is -4. If you wanted everything to be positive, so if you added 5 to this, and if you added 5 to this, right, and if you added 5 to this, right, so everything becomes positive edge weights, right? So and then you actually get that this is indeed the shortest path, right, in this positive edge weight graph, but in the older graph, it is the one which has 2 plus 5s which are added, which is actually the shortest path, right? So therefore, that also doesn't work. Okay, so this one, I'll just take this back. So this is wrong. Other questions? You can also try and see if you don't worry so much about the heap here, right? You can see that you just have to pick the minimum valued element from an array, right? And you can get an easy n square kind of an algorithm, but that's something that we don't worry about. So we just assume that the values are stored in the heap.